Okay, then I will start. Thank you very much. My name is Dennis Neumüller, and I'm presenting the paper Exploring the Effectiveness of Abstract Syntax-Free Patterns for Algorithm Recognition. What is algorithm recognition about? Our goal is to identify the implementations of algorithms in the software system. That means that we are given a source code base that is unknown to us, and we're interested in finding all of the algorithms implemented and the components implementing these algorithms via static analysis. What are use cases for algorithm recognition? Why is this useful at all? One of the use cases could be software improvement. We could detect inefficient algorithms, for example, bubble sort, and try to replace them with a library call and an efficient implementation. We could detect common bugs and inefficiencies in algorithm implementations, for example, the choice of the pivot in quicksort, or we could try to verify that all the edge cases are handled in binary search. And we could do this in terms of a continuous integration pipeline, similar to tools like TeamScale or SonarQube that are already used. Another use case is supporting software understanding and software reverse engineering. Typical problems in these domains are that it's a tedious, time-consuming, and often manual process. Colleagues and experts are not available because they've left the company or they have a lot of work to do, and usually the documentation is out of date. This means that the source code is basically the ground truth, and it would be very helpful if we could extract information from the source code. For example, we could extract high-level information such as what is the application all about, what is happening here, are we doing image processing, are we doing cryptography, are we doing compression, or are we in a context of a distributed system? We could also try to extract low-level design decisions. For example, which specific algorithms are used? For example, are we using Paxos or Raft in our distributed system? We could also detect properties of these algorithms, such as is a sorting algorithm stable or unstable, or properties that pertain to all algorithms like time complexity. What is related work in this area? And there are some approaches from the area of cliché recognition, which are also interested in identifying abstract structures in the source code, and are also using search patterns. However, they suffer from scalability and usability issues, and their patterns are not evaluated. Additionally, they focus only on very simple examples, such as in sequential search through a data structure, which is basically just a for loop. Approaches from the area of code search range from simple text-based tools to dedicated code search languages. However, they do not focus on algorithm recognition, which means that their expressiveness is limited, and they also miss many features which we consider important for algorithm recognition, such as allowing multiple queries, abstractions for finding algorithms, or features like the matching order of statements. Finally, we have code clone detection tools. Two pieces of source code that implement the same functionality are clones of each other's, but these tools do, however, have no support for queries, which means that we cannot specify the key features of algorithms. Additionally, as we will see later on, they only achieve limited results. What are the contributions of our paper? We developed a pattern language to designed to describe key features of algorithms. Using our language, we created search patterns for 5 common algorithms, including prime factors, Fibonacci, palindrome, bubble sort, primary search, and GCD. We implemented a matcher to find these algorithms in source code, and we performed an evaluation using the Big Clone Evil dataset, comparing ourselves to large language models and code clone detection tools. In this talk, I will focus mostly on the pattern language and evaluation. Let's assume that we're interested in finding implementations of the greatest common divisor algorithm, such as the one presented here. However, there's a lot of variability in implementations, even for a simple algorithm like this. For example, we could rename identifiers like the variables or the method itself. We could swap the order of parameters, or we could swap the order of the operands for commutative operations like equality. We could make the else explicit instead of relying on an implicit early return, or we could use a completely different implementation that uses repeated subtraction in a loop instead of a modulo operation. And all of these implement greatest common divisor. In the following, we will use a pattern language and try to include as much of the variability in the search pattern as possible. The basic elements of a language are builder objects that mirror the individual Java language constructs, such as the method or the parameter builder we can see on the left. These builders can be configured to specify the desired search pattern. For example, in this case, we configure the method to require 2 parameters. And we've seen one point of variability are the names of elements in the source code. And therefore, we abstract from these names by using bindings and specify our own identifiers. During matching, these identifiers will be bound to the matched AST element. In this example, the method definition will be bound to the identity of the method and therefore to our identifier M. By reusing the identifier multiple times in the search pattern, we can refer to the identity of the same AST element independently of its name, which makes us robust against renamings. Another point of variability is the order of parameters. Therefore, we use the hasParameters construct in our language, which specifies that we want to allow the matching in any order. Afterwards, we configure the body of the method, where we expect an if statement and a condition, where we want the comparison with a variable in the literal 0. During the matching, our variable read will match and bind the variable b. And since we will use the variable read multiple times throughout the search pattern, we can extract it to the top and later reuse it. We've also seen that the equality comparison is one point of variability because it's commutative and we can therefore change the order of the operands. We allow this in our search pattern by configuring compare commutative. And then we require a return statement, returning the variable which matches A. Some implementations of GCD make the if-else explicit instead of relying on the early return. We therefore also configure an optional else statement in our pattern, which means that the else may be present, but is not required for a successful match. And we specify the last return statement now, where we want a method call binding the same identifier we used previously for the method declaration, and therefore ensuring that the call is recursive. And finally, we expect the arguments where we want a variable read binding b and the modulo division. Our search pattern now matches almost all of the identified implementations. In the last extension, we want to also include the iterative variant. Since this one is quite different, we add an alternative in the method body using the one-off statement, and we specify the iterative and the recursive part as options. We would now specify the recursive variant in a similar fashion as previously, and while doing this, we can use many parts of the search patterns that are identical, for example, the variables or the method definition. In summary, our AST-based language is designed to describe only the key features of the algorithm's intent variability. By embedding the language in Java, we gain many usability features such as code completion, inline documentation, syntax and type checking, modularization and reuse, and debugging support. In the following, I want to shortly talk about the matching procedure and explain the basic idea of our approach. Given the search pattern, we first transform it into a pattern tree. We then pass the Java code into an abstract syntax tree using the Java library Spoon. Afterwards, we perform that first search, starting at the root node and basically comparing each node of the pattern with its counterpart in the abstract syntax tree. And if this succeeds, we have found a match of a search pattern. We evaluated our search patterns on the Bigclone-Evil dataset, which contains manually verified algorithm implementations from 25,000 open source projects. And we posed the question, how well can algorithms be detected using our S-based pattern language? As this is a classification task, we use the typical classification metrics in an evaluation. Take off where I left from and try to summarize the table. As we can see, we have a good recall overall, and we also have good precision. There are two problematic search patterns. One is GCD, where we have a little drop in precision. This is due to the case that we specified the search pattern too permissive. For an improved version, we would now include more constraints into this search pattern. And the binary search pattern, which is the opposite, we have good precision, but we do not find all of the implementations. This is the case because we based the search pattern on only 2 reference implementations, which was not enough to find all of the typical ways of implementing binary search. And therefore, the conclusion for research question 1 is that a S-based approach is suitable for algorithm recognition. Our patterns achieve solid performance for most algorithms, but binary search shows that reference implementations are important when deriving the search pattern. We also compared ourselves to large language models. As we've seen in the keynote, large language models have seen an impressive boost in capabilities in recent years and are now used for a whole range of code-related tasks, such as code generation, summarization, or code clone detection, and bug fixing. This also motivates them for using them for algorithm recognition. We therefore selected CodeLlama, which is a widely used large language model, fine-tuned specifically for code-related tasks, and posed research questions, how well do our results compare to the large language model? We iterated over every method in the dataset, asking the LLM if the method implements the algorithm, very similar to the previous presentation. However, this yielded a very low F1 score. We therefore also applied context learning, where we provided the large language models with a positive example and a negative example for each algorithm, which massively improved the F1 score. As we can see, the large language model has a very good recall over all the algorithms, but poor precision because it generates a lot of false positives. Additionally, applying the large language model to the dataset takes very long, and therefore we can conclude that our search patterns achieve similar recall, but are more precise than the large language model, which results in a better F1 score. Additionally, our search patterns are also significantly faster than the large language model. We also compared our search pattern to code clone detection tools as a baseline. Motivation here is that different implementations of the same algorithm are clones of each other. Therefore, code clone detection tools could be used for algorithm recognition, and we are interested in finding out how do our results compare to these code clone detection tools. We selected different widely used code clone detection tools such as SourceRSSE and CloneWorks, which are token-based, NiCAD, which is a hybrid approach, and Oreo, which is machine learning-based. Additionally, NiCAD and Oreo focus on the detection of type 3 and type 4 clones, which are harder to detect due to their syntactic differences. Our results show that our search pattern have a higher recall, and we achieve a recall of 0.62 versus only 0.2 for the best code clone detection tools. The code clone detection tools struggle especially with type 3 and type 4 clones because they're harder to detect. And this means that code clone detection tools would be quite limited when used for algorithm recognition. The overall conclusions from our paper are that ASP-based search patterns work quite well, at least for simple algorithms. We now know that a good set of reference implementations is important, however, and code clone detection tools are quite limited when used for algorithm recognition. In future work, we would like to include data and control flow analysis in our tooling and see if this can further improve our patterns. We'd like to investigate the automatic generation of search patterns based on reference implementations, and of course, would like to validate the results with more complex algorithms. Thank you for your attention.
Any questions? I asked already the question in the Zoom, so Dennis, thank you for answering the question. I've written a few more, but take your time to answer those. Thank you again for your talk.
Okay, I will answer those in Zoom.
Look like you're criticizing LLM on this conference a lot. They're not as good as this, they're not as good as that.
It's interesting that everybody uses and tries to use them though, and the results that are quite counterintuitive sometimes.
People keep verifying that and confirming that their performance is worse than expected. It's interesting. Okay, Dennis, thank you very much. We're finishing our conference on time.